Hi everyone, my name is Ritvik Sharma. Thank you for the introduction, Robert. My work is on compiling qubit circuits to optimize qutrit circuits, and this work was done at Stanford with Professor Sara Achour. Generally speaking, quantum computing is done with these devices that have two energy states or levels. They're called qubits. But in reality, many quantum hardware technologies used to implement qubits can actually support an infinite number of energy states. They're called qutrits when you use 3 of their states, qquats when you use 4 of their states, and so on, generally being referred to as qubits for D states. Qubit-based computing just constrains us to using the first 2 energy levels, whereas the higher energy levels or states are left alone. So using the same or in the same qubit circuit that we've seen up till now, we can actually access these higher energy states for computation as well. But the question is, what does that really give us? For that, we'll take a running example of a Toffoli gate. This is a double-controlled X gate, so it applies an identity if the first 2 qubits are 0, 0, 0, 1, and 1, 0. And it applies an X gate if they're in state 1, 1. Unfortunately, though, you can't directly implement many quantum operations like the Toffoli gate here onto a qubit hardware platform directly. Instead, you need to break it down into a complicated circuit implementation that has several gates from a standard gate set. For example, for the Toffoli gates case, you will need the standard implementation that has a bunch of single qubit gates and CNOT gates. So here's the Toffoli gate again, and the standard qubit implementation on the left. So the question is, can qubits help in building more efficient circuits for such cases or such problems? I guess the title gives it away. Here, using qubits, you can implement this same operation with much smaller depth as shown on the right. This implementation is much shorter because it's able to utilize this higher energy state, the 2 state here, as temporary storage. And it's not just the Toffoli case. There are many other gates or circuit implementations that have been manually figured out in prior work. Unfortunately, though, not many automated solutions exist to target such implementations. Current quantum compilers mainly focus on qubits. Their approach can be used for qubits, but only for very restricted cases, like, for example, D is equals to 4, which is a device called a qquat. This is only possible because you can take a 4-level device as a collection of 2 different qubits. So you use your standard qubit compiler and combine 2 qubits together into one single qquat. But this approach doesn't really work for most qubit cases, shown in red here, which are not exactly a power of 2. In particular, qutrits, which have 3 states and are hence more stable than qquats and have been demonstrated somewhat successfully in hardware, cannot be targeted. That's where DARE comes in. DARE starts off with a qubit computation and optimizes it by converting it into a qutrit circuit that applies the same qubit transformation that you wanted earlier, but using the qutrit states intermediately. For the logical Toffoli example, in this case, DARE will generate the efficient qutrit Toffoli that you saw before. Since DARE circuit outputs are meant to be used as an implementation of the original qubit circuit, they're meant to be used with qubit states, that is, like with binary input and output states, binary being a superposition of 0 and 1. Therefore, the result, going next, so any circuit interface for any DARE output would be binary. We name such qutrit circuits with binary interfaces as qubit-qutrit circuits. DARE compiler has 2 main components. First is the decomposition step, and the second is the rewriting step. This is all followed up by a lowering pass that implements the optimized logical circuit into a basis gate step. The first challenge we have here is to convert the original qubit computation into a circuit that uses the 2 state in the first place. So DARE converts the initial qubit circuit, which has a qubit unitary, that is of size 2 to the power n cross 2 to the power n for n qubits, into a qutrit unitary, into a naive qutrit circuit that doesn't really use the 2 state, but it does now have a qutrit unitary, which is of size 3 to the power n cross 3 to the power n. Next, we decompose this unitary using our own novel extension to quantum Shannon decomposition, which uses cosine sign decomposition under the hood to break this matrix down to build a circuit that uses the 2 state. This circuit now uses all 3 qutrit states, and this circuit is also strictly equal to the original lifted qutrit circuit. By strict equality, we just means that the unitary applied by these circuits are exactly identical. So coming back to decomposition, you notice that the decomposed circuit is not really the optimized circuit we promised from DARE. So what's next? That's where DARE implements a series of rewrites to optimize this decomposed circuit to give you the final circuit by deleting a bunch of gates and controls. First, like most rewrite systems, we contain a bunch of 6 strictly equal rewrites. These rewrites optimize a circuit without changing the underlying computation, that is the unitary, applied by the circuit at all. Using only strictly equal rewrites, we start from the decomposed circuit and delete the gates at the end and get this circuit here. You again see that it's still not all the way there, and this is not enough for optimization of qutrit circuits in general. So what can we do more than strictly equal rewrites? DARE solves this issue by implementing a series of novel rewrites that don't preserve strict equality of the circuit, but instead they preserve a novel notion of equality that maintains the actual operation being applied by this circuit for binary input and output states. And these rewrites are hence more relaxed and allow for more aggressive optimization. Showing that for the Toffoli example, you'd see we notice more gates and controls now and get this circuit, which is exactly the same as the optimized circuit that we were promising. We call this equality property as qubit equality. Here's the comparison of the final circuit from using only strictly equal rewrites and qubit equal rewrites. So let's try and understand why qubit equality makes sense. Here's the unitary of the qubit circuit and the qubit qutrit circuit. The qubit qutrit circuit uses the 2-state only temporarily. Thus, if we drop all the rows and columns of this unitary that interact with the 2-state, that is ones whose base 3 index representation has a ternary or 2 value in them, then we get back the original qubit unitary. So there's a lot of degree of freedom in the qubit qutrit unitary that we need to utilize during the rewriting or optimization process. DARE rewrites exploit this very freedom to optimize the circuit while maintaining qubit equality. We verify qubit equality using the unitary of the circuit before and after the transformation. Earlier, you saw a linear algebra interpretation where we drop all those rows and columns and show that those unitaries just need to be the same as the original qubit computation. However, formally, for proving our rewrites, we use an outer product notation to write the unitary of the circuit before and after transformation and ensure that the difference of these unitaries is dependent on at least one of those qutrits being initially in the 2-state. Again, since the circuit interface was binary, this difference will never actually be seen on the circuit output for any valid input. Hence, if delta U is dependent on the 2-state, as shown with the Dirac outer product notation here, qubit equality is maintained. This is on contrast with strict equality, where the unitaries are exactly equal. Let's walk through an example of DARE rewrites and how we go about building and proving them. Our rewrites are built as a collection of these manually specified basic transformations. Each transform has 3 components. First are a set of necessary gate conditions. Second is the transformation applied if these conditions are met. And finally, a transform comes with a proof that shows that it maintains stricter qubit equality. Let's walk through an example. This is a transformation called CC inter, and it preserves qubit equality. For it to maintain qubit equality, it requires a pair of gates that are applied together on the circuit called bookends that modify their target qutrit k from being subsetted to a binary basis, that is a superposition of 0, 1 states, to a ternary basis, a superposition of 0, 1, and 2 states, and vice versa. A bunch of intermediate gates between them share with them a common control, as shown with the value C here. And the intermediate gates are controlled on qutrit k on state 2. Then the transform deletes the shared control from the intermediate gates. Now, let's walk through how we prove any transformation, especially CC inter here, for our transforms. We use the outer product notation to write the unitary of each gate, and when we multiply them in the reverse order, we get the unitary of the fragment itself. The outer product notation allows for a symbolic representation of arbitrary controls for the rewrite. Now, let's take an example of a control gate inter, the one in between. As you know, the control gate is only applied when all the conditions are met. So for each control condition, we have these matrices actually that have just one element, which is shown with the bracket notation here. For the given control conditions, the target unitary U prime prime is applied. And if a qutrit is skipped, you just apply an identity on it. But we also need to add to this what happens when the control conditions are not met. For that, we add the rest of our normalization term and rewrite it into this form shown here. Going next. CC inter deletes the intermediate gates control, that as we were saying for this example. So for that one control qutrit, we just replace that control term by an identity. And now, this was just one gate. You need to do this for every other gate and find the overall unitary of the circuit. But using the unitary definition, and also we need to remember that what we need to prove is this particular transformation preserves qubit equality. That's the definition here. What we find is that we don't need to actually multiply these unitaries together. Instead, because the ordering of the gates is captured by the unitary definition, we can simplify it out by factoring gates and doing some other rewrites, or rewriting this equation a bit, and find what the delta U is, and show that this difference exactly matches the qubit equality definitions, which you can pattern match with the different colors here. Hopefully they're visible. Of course, exhaustively proving these transformations can be more detailed. The proof accounts for different types of gates being before or after the bookends, and for arbitrary gates being added between the bookends as well. For any gates before and after the bookend, we use the fact that the circuit transformation conditions restrict the transformation from being applied arbitrarily and help in holding up our proof in those cases. And for gates, in cases of different kinds of gates in between the bookends, we use induction to prove for arbitrary cases. However, this implementation has one issue. That is that DARE starts off by decomposing unitaries. So this step needs to break down matrices of size 3 to the power n, which scale up in size exponentially. So for larger circuits, DARE simplifies this issue by partitioning the circuit into smaller sections with fewer number of qtrits each. This creates a much simpler decomposition process, after which the circuit can be assembled back together to apply rewrites, allowing them to occur across circuit splitting boundaries as well. We evaluate DARE's generated circuits for circuit complexity and fidelity. We compare against 3 baselines. First are a bunch of manually built qubit circuits where each Toffoli implementation is replaced with the qubit Toffoli standard implementation that we saw. Second is quartz, which uses super optimization to optimize qubit circuits. Second is, and finally, we have manual qutrit circuit implementations. One set of our benchmarks have been previously hand implemented using qutrits before in literature, and second set of our benchmarks contain a large number of Toffoli gates which can be replaced with the efficient qutrit Toffoli. Comparing generated circuits against qubit hand implementations, we find our circuits can have up to 75% smaller depth and up to 65% reduction in 2 qubit qutrit gate counts. Comparing against quartz, we improve depth by up to 63% and 2 qubit gate counts by up to 56%. Overall, DARE beats quartz for most benchmarks and marginally underperforms for just one case. The reason is that we are able to utilize an extra degree of freedom that quartz unfortunately just cannot, because of the fact that we're using qutrits here. So we also compare DARE against manual qutrit implementations. On the left, we have benchmarks that have previous hand implementations, and on the right, the benchmarks that I mentioned, which have a large number of Toffoli gates. We find that our implementations can see up to 65% reduction in depth and up to 64% reduction in 2 qutrit gate counts. Next, we see if these circuit complexity improvements actually translate to fidelity improvements with qutrits. Here, we need to consider the fact that qutrits use a higher energy state, which is inherently more erroneous, and hence, we need to take that into account for modeling fidelity. For doing that, we assume a symmetric error channel where the gate error scales up in proportion to the number of error channels. Hence, qutrit gates for this model can be up to 5 times more erroneous than the qubit case. And we also model idling errors for decay between states. Overall, we find that we evaluate fidelity for qubits, hand qutrit, and DARE qutrit implementations, and overall find that DARE improves upon manual qutrit implementations by up to 9 times. However, since error for qutrits is scaled up in comparison to qubits, qubit circuits, even when you're using DARE for qutrit circuits, can have up to 61% better fidelity. So significant effort in qutrit hardware design may be required for translating the circuit complexity improvements that we see with qutrits to fidelity improvements. To evaluate exactly how far we can get with this, we check a case where we make both devices equally erroneous in terms of their gate errors, keeping the idling error the same, and find that DARE circuits in this case can get up to 7 times higher fidelity. Thus, with more stable, higher energy states, you can get less erroneous and less complicated circuits in the future than what we have right now with just qubit circuits. Overall, our system is the first compiler that can directly target non-base 2 systems. It is able to perform rewrites by exploiting a novel notion of equality while being competitive to hand implementations. We use an outer product notation to prove these transformations for correctness. And furthermore, while current hardware doesn't really show improved fidelity, projected results for qutrits can be much better. Thank you.
Thank you. People can line up in the middle to ask questions.
Hi, thanks for the great talk. What would be involved to generalize the techniques in DARE to higher qubits like qquarts and qquints? And how do you expect DARE to compare to existing tools for qquarts?
Yeah, I think, yeah, that's a great question. So I think the question is basically about if we extend this, like this like tool chain to like account for different types of qubits and how it compares with the existing qquart compilers, right? So I don't have the answer to how it would compare against qquart compilers because I have to like go in, like try it out and figure out what would happen in that scenario. But I feel like extending it for arbitrary cases of qubits is fairly feasible because it requires translating the. So right now, if you would notice, the annotation that we're using is the fact that the circuit interface is binary. And what we do in reality is we project this out to figure out what portions of the circuit are restricted to these binary subsetted states. For a qubit case, for an arbitrary qubit case, you just need to extend that for binary, ternary states, quaternary states, and so on, depending on the kind of gate being applied, or being very choosy on like what particular states you're annotating in your circuit, in your static analysis there, for doing the optimization. So it would basically expand the set of, like the representation of the circuit slightly, and accordingly the transformations being done. And as far as the qquart compiler question goes, I think it would mainly depends on how far you can get with the decomposition as well, because the decomposed circuit needs to deal with these larger and larger matrices as you go along. So after one point, I'm guessing it could get fairly involved and get more complicated than, like, might not be feasible after like a certain value of d, just because of the fact that we're using this nuclear option of decomposition. So, yeah.
Thanks again.
I have a question about your optimizations.
Yes.
Are you relying on that the qtrit is in a particular well-known state, or can you optimize based on something dirty that you return to that state after the optimization?
I'm not sure if I understand the question. Is the question that like...
So if it was a qubit question, I know how to ask it. So it's like you only optimize based on a helper qubit if it's known to be, say, ket 0. And then you return it to be ket 0 afterwards. But sometimes optimizations can deal with that the helper qubit is in an arbitrary state, and you return it to that state after you're done. Can you do something similar for the third level, where it's in something arbitrary amplitude or something, and then you return it to that after the optimization?
The arbitrary amplitude. I think so. The question would basically, so that would basically, I think that would what that would translate to for this particular scenario. Would be like one particular qtrit not being in the binary state, but being in a subset of like, let's say 0 and 2 states.
Yeah.
Then I would just need to change the annotation that I'm making from being 0, 1 states everywhere. Or so right now what I do is like annotate it as 0, 1 states, and in certain cases 0, 1, and 2 states. But we have the ability to annotate them as other states as well, and just use that particular annotation for doing this transformation. Of course, in our cases, because everything was binary, those annotations were never really used as much.
I see.
Thanks for a great talk. So basically, you are talking about if we have a qubit circuit, and if we are implementing the same gate, we have some advantages in the qtrit circuit compared to the qubit circuit. Is that right? But I was thinking, do you consider that? Because I know for some gate they have some really smart decomposition based on the qtrit circuit. Do you comparing your optimization method to those smart decomposition method? Because I know there's something published in the Nature Physics about large thoughtfully decomposing using the qtrit circuit, and they have really nice result. Yeah.
Yeah. So I think the question would just basically become, how do you implement like large Toffoli decompositions?
No,
into
I was thinking you are compared to the qubit circuit.
Yeah.
How about you compare some smart decomposition, but they are originally using the qtrit circuit? That's why you can say you are optimizing something, right?
Yeah, so that's where our comparisons against previous hand implementations come in.
Okay.
Where, if I can go to the slide, and one set of our benchmarks basically were some of the benchmarks that have been hand optimized with qtrits before.
Yeah.
That include like something like a 3-qubit Toffoli to a 4-qubit Toffoli and incrementer operations.
Okay.
So I think it's further up. Sorry, let me just. So yeah, the set of benchmarks that we used were basically those implementations. Of course, because we're using decomposition. The one unfortunate aspect of that is we can't directly decompose an arbitrarily large Toffoli to do this kind of an operation for like, let's say a 14 qtrit circuit or something like that. So, and I guess one solution to that might be in the future would be to just take a qubit implementation of it and partially decompose it for different sections, the same way we were doing for other circuits at the end here. So, yeah.
Okay, thank you. Let's sync up with the speaker again.